Hi everyone! Today we're continuing Chapter 19, Electrochemistry. So last time we saw how to balance half reactions for an oxidation-reduction reaction. And we saw that sometimes it's really easy, and sometimes it's a little more difficult, especially if we have to balance oxygen atoms and then hydrogen atoms, etc. And that also depends on whether we have an acidic solution or a basic solution. Now, today we're going to shift gears a little bit, and we're going to focus more on the transfer of electrons and how we can use that in devices such as batteries. So, electrons flow through a conductor in response to an electrical potential difference. So, electrical potential difference. And this is similar to water flowing downhill in response to a difference in gravitational potential energy. So, electrons, similar to water, can flow as long as they can flow in a spontaneous way. Now, sometimes we can force them to flow in a non-spontaneous way, but typically we want to use as little energy as possible for an electron transfer. So an electric current is the amount of electric charge that passes a point in a given period of time. So maybe electrons are flowing through a wire. So down below we have a picture of a wire. There's a negative end and a positive end, and electrons are negatively charged, so they're going to be attracted to the positive end. And as they're flowing through, maybe we have a meter hooked up to that wire, and it can detect how many electrons are passing that point during a given period of time. Now, another way for electrons to flow is through a solution. So we'll talk about examples of that in a second. And then even further down below, we have a picture of water flowing due to gravity. And again, this is very similar to how electrons flow, but instead of gravity affecting their flow, it's a potential difference that's causing them to flow. So here's an example of how electrons would move in a solution. So up above we have a zinc strip of metal, and it's placed in a copper 2 sulfate solution. So that would look like this in its chemical formula. Now, over time, electrons are going to spontaneously move in this solution. So down below, we have the equation for what's occurring here. So originally we have pure zinc, so that has an oxidation number of 0. And then we have copper ions, which are coming from copper sulfate. So remember, when copper sulfate dissolves in water, we end up with copper 2+ and sulfate ions. So copper 2+ is just coming from copper sulfate. So its oxidation number will be +2. And then what happens is electrons are transferred from zinc to copper. So we end up with zinc 2+ and pure copper. So if zinc is going from pure zinc to zinc 2+, is zinc losing electrons or gaining electrons? And I kind of already gave it away. So it's losing electrons, right? And in fact, it's losing 2 electrons. And then as copper 2+ turns into pure copper, which is neutral, is copper gaining or losing electrons? Gaining electrons, right? And it's actually gaining 2 electrons from zinc. So then we get our overall reaction shown below. So in the picture up above, you'll notice that the zinc atoms, which are pure solids, they're going to give up their electrons to the copper ions. And then the copper ions become neutral copper and deposit themselves on the surface of the metal strip. Now the zinc, because it's lost 2 electrons, is actually going to leave the surface of the metal and end up as ions in solution. So up above, you can see that there's some sort of black deposit on top of the zinc, and that is the pure copper. All right. Now we can utilize this spontaneous redox reaction to maybe power something like a battery, because in this process we do have a flow of electrons going from zinc to copper. So what we can set up is something called a voltaic cell, or sometimes we'll call this a galvanic cell. So down below we have, instead of copper and zinc in one beaker together, we're going to separate them. So we're going to put zinc in its own beaker, and we're actually going to place that zinc metal in a solution of zinc nitrate. So not only do we have pure zinc, we also have zinc 2+ ions present in that beaker. Then in the other beaker, we're going to place pure copper in a solution of copper nitrate. So we have pure neutral copper and copper 2+ ions. Now you'll also notice that there's a wire connecting the two beakers or two metals together, and that's what electrons are going to flow through. All right, and remember that zinc is naturally going to lose 2 electrons. So you'll notice this zinc atom over here, it's losing 2 electrons, and those are actually going to go up into the wire. And then the electrons again are going to travel through the wire, and they'll end up in the opposite beaker, and they're going to help form pure copper. So copper 2+, which is in the copper nitrate solution, is going to grab onto those 2 electrons and become neutral copper. So it's the same thing that we saw before, except we've placed copper and zinc in different beakers. Okay, so now you'll also notice a couple of other things. You'll notice that there's a light bulb set up along this wire. And remember, if we have a movement of electrons, we generate a current. And that current can produce electricity that will power the light bulb. Now, there's also what's called a salt bridge. So this salt bridge in particular contains potassium nitrate. And you'll notice that the potassium ions are attracted to the copper side of our setup, and the nitrate ions are attracted to the zinc side of our setup. So on the left-hand side, you'll notice that zinc is producing zinc 2+ ions. And those zinc 2+ ions need to bond to something. So they're going to bond with those nitrate ions that are coming from this so-called salt bridge. And then on the right-hand side, we're producing pure copper, so we're losing positive ions from solution. So these potassium ions in the salt bridge are going to replace the copper ions. And then at the bottom of the salt bridge are some glass wool plugs, and those are going to allow ions to pass through without letting too much of the other solutions pass through. Okay, so let's talk about this in a little more detail. So oxidation and reduction half reactions in an electrochemical cell are kept separated. And each half reaction will take place in its own cell, which we'll call a half cell. So again, oxidation and reduction half reactions are kept separate in half cells. And then we saw that electrons will flow through a wire along with ion flow through a solution. And this is what constitutes an electric circuit. So electrochemical cells require a conductive solid electrode to allow the transfer of electrons. So that's going to be the metal that we saw. So the electrodes are zinc and copper. So those are our two electrodes. Now the electrodes can take different forms. So we might use, for instance, graphite, which is just the what we call pencil lead, but that's kind of a misnomer because the pencil lead, quote unquote, is actually graphite. And we'll talk more about that later. But we do need some sort of solid in order to allow the transfer of electrons. So here I'll write down below copper, zinc in previous example. Okay. And then, of course, we do require ion exchange between the two half cells. So that's going to involve an electrolyte. And the electrolytes are the zinc 2 plus ions, and then we also have nitrate and potassium as well as copper. So we've got quite a few ions passing around this solution. All right, so you might have also noticed there were a couple of labels in our figure, anode and cathode. So the anode is the electrode where oxidation always occurs. And this will be the more negatively charged electrode in a voltaic cell. So if we go back to our picture, you'll notice that zinc was labeled as the anode, and it is negatively charged. Now you'll notice that copper, on the other hand, is labeled as the cathode, and it is positively charged. And then you'll also notice electrons are moving from the negative side, the anode, to the positive side, the cathode. And that's just due to the fact that opposites attract in terms of charge. So electrons are attracted to the positive charge of the cathode. All right, so again, the cathode is the electrode where reduction always occurs. And this is the more positively charged electrode in the voltaic cell. So there's a couple of ways that I used to use to remember this. Sometimes I just thought about it in terms of oxidation has a vowel at the front, an O, and anode has a vowel at the front. So those two go together. Whereas cathode and reduction, those have consonants at the front. So I don't know. That's one way that I remembered it. The other way that you can remember the charges for them, so remember cats are positively charged. So the cathode will be positively charged. whereas the anode is negatively charged. That's one way I kind of remember it. If you have a better way to remember those different terms and which ones go together, whatever works for you, that's fine. All right, now we also saw that salt bridge. So that's an inverted U-shaped tube that contains a strong electrolyte. And that's what connects the two half cells together. So remember, we were using potassium nitrate, and that was splitting up into potassium and nitrate ions. And these ions were flowing to opposite sides. So the potassium ions were replacing the copper ions, and then the nitrate ions were joining up with the new zinc ions that were forming. All right, so if your redox reaction involves oxidation or reduction of an ion to a different oxidation state, so maybe you have copper 2+ and it's turning into copper 1+, for instance, or the oxidation or reduction of a gas, we may use something called an inert electrode. So an inert electrode is one that does not participate. Oh, these words are flipped. English is hard. So it's one that does not participate in the reaction, but just provides a surface on which the transfer of electrons can take place. So sometimes we're not going to use two metals like copper and zinc. There might be some situations where the electrode isn't easy to come by, and then we need something different. So as an example, here we have a overall reaction between iron and copper. So iron 2+ is becoming iron 3+. So it's being converted into a different charged state. And then copper 2+ is being converted into pure copper. So on one side, we will use just regular old copper as our electrode, and it's the cathode. And then on the left-hand side, because iron is starting out as an ion, it's not starting out as pure iron, we don't really have solid pure iron that we can use in solution without it completely dissolving. So instead, we're going to use something called an inert electrode on that side, and that is platinum. Now, sometimes you can also use things like graphite, which we mentioned earlier. And graphite is probably cheaper and easier to come by, but platinum is also a pretty common electrode. And that would be our anode. Okay, so how did I know that copper was on the cathode side and platinum was on the anode side? Or the iron was on the anode side. So iron is, again, starting out as a 2+ ion, so its oxidation number is +2, and then its oxidation number in the products is +3. So is that losing or gaining electrons? It's losing an electron, right? So if it's losing an electron, is it oxidized or reduced? It's oxidized. And then what about copper? Copper starts out as a +2 ion, so its oxidation number is +2. And then it becomes a neutral atom, so its oxidation number is 0. So is it losing or gaining electrons? Gaining electrons. So then is it oxidized or reduced? Reduced. Now remember, oxidation occurs at the anode, and reduction occurs at the cathode. All right, so then we know that the iron oxidation will be on the left-hand side. It will be the anode. So that's where electrons are going to be produced. And then they're going to flow through the wire over to the cathode, which again, remember, is positively charged, whereas the anode is negatively charged. So electrons are naturally attracted to that positive side. All right, and so the copper ions in that solution, they're going to grab onto 2 electrons and then become neutral copper. And they'll just deposit themselves on top of that copper cathode, or that copper electrode. Okay. So hopefully this is starting to all come together a bit. Just a couple of technical things. So we said that we have an electrical current running through the electrochemical cell, or the voltaic cell. Current is the number of electrons that flow through the system per second. So the unit that we use for current is called the ampere, or you might hear it as amps. And that has the symbol capital A. So 1 amp of current is equal to 1 coulomb of charge flowing through each second, or flowing each second. So coulomb has a symbol capital C. And what this really tells us is that 1 amp is equal to a certain number of electrons per second. So that's 6.242 times 10 to the 18th electrons per second. So that's a lot of electrons. So this will be a key factor there. And then the difference in potential energy between the reactants and products is called the potential difference. So remember, a long time ago we talked about kinetic energy versus potential energy, and kinetic energy has to do with motion, whereas potential energy has to do with the relative position of an object or of reactants. All right, so the unit for potential difference is the volt, which has the symbol V, and 1 volt is equal to 1 joule of energy per coulomb of charge. So really all this is telling us is the voltage needed to drive electrons through the external circuit. So how much energy is needed, or how much energy does it take for electrons to move? Okay, so let's do a quick example problem. So the current running through a wire measures 4.5 amperes. How many electrons are passing through the wire per second? All right, so let's start with what we know. We have 4.5 amps. And we need to convert that into electrons per second. So on the previous slide, we saw that 1 amp is equal to 6.242 times 10 to the 18th. And that's in electrons per second. So let's write that down. And I'm just going to put electrons as my unit in the numerator. Or actually electrons per second, sorry. And then in the denominator, we're going to put 1 ampere, or 1 amp. All right, so now let's plug this into our calculators. And I actually Don't know where my notes are, so I'm just going to do this off to the side. So 4.5 times 6.242 times 10 to the 18th. Let's see. So that should give us 2.8 times 10 to the 19th electrons per second. And I limited my answer to 2 significant figures because that's how many sig figs we had in the beginning. And remember, with multiplication, we always want to limit our answer to the fewest number of sig figs or the least accurate measurement. All right, so that conversion isn't too bad. So now let's talk about that cell potential. So we said a couple of slides ago that the difference in potential energy for an electrochemical cell is the potential difference. So let's go back. So remember, the difference in energy between the reactants and products is the potential difference. So now we can actually call that the cell potential. So I kind of like to think of it as, what's the likelihood that this electrochemical cell or this battery will produce energy? What's the likelihood that electrons will flow from one side to the other? So that cell potential depends on how easily the oxidizing agent is reduced at the cathode and how easily the reducing agent is oxidized at the anode. So if one side doesn't oxidize very easily or the other side doesn't reduce very easily, then we're not going to have a significant flow of electrons. So the cell potential would be quite small. But if both sides oxidize or reduce really, really easily, then we're going to have a higher cell potential or more electrons flowing. So we call the cell potential under standard conditions the standard EMF. So EMF is electromotive force. Now, the electromotive force under standard conditions is given the symbol capital E, and then we just put a little cell next to that. And we also use a degree symbol to indicate that this is under standard conditions. Now remember, for standard conditions, the temperature is 25 degrees Celsius. Gases are at 1 atmosphere of pressure. The concentration of a solution is 1 mole per liter. And let's see, I think that's it. All right. So this E cell value is equal to the sum of the cell potentials for the half reactions. So these cell potentials for the half reactions, we're just going to call those E. All right, so one more thing about electrochemical cells. There is a way that we can represent what's going on with a certain type of notation. So instead of having to write out both half reactions or the overall reaction, we can just simplify it or summarize what's happening with this electrochemical cell notation. So in our figure on the left, we have the anode, which has pure iron. And then we have the cathode, which is platinum. So let's see. So we had to use platinum on the right-hand side because the half reaction involves uh, permanganate as an ion, and then manganese in that reaction is going from a +7 oxidation state to a +2 oxidation state. So we don't have neutral manganese available for this particular half reaction. So we're just going to use platinum instead. So up above it says, because the half reaction involves reducing the manganese oxidation state from +7 to +2, we use an electrode, so platinum, that will provide a surface for the electron transfer without reacting the permanganate ion. All right, and the reason we want to use platinum here is it works really well because it's extremely non-reactive but still conducts electricity. So the platinum is not going to react with permanganate, it's just going to help transfer electrons. All right. So what we can see here is that the iron is going to give up electrons, which will flow through the wire here over to the cathode, which is platinum. And then those electrons, so we're actually going to see 5 electrons react with permanganate and 8 hydrogen ions to produce our manganese ion and water molecules. Now, the way that we can summarize these two reactions is shown down below. So on the left-hand side, we have our oxidation reaction. And then on the right-hand side, we have the reduction reaction. So on the left-hand side, we're showing that solid iron is going to become iron 2 plus ions. So we're going from a solid to something that's aqueous. And we're separating those two different states of iron with this line. Then we're going to separate the oxidation reaction from the reduction reaction with 2 lines. So there's 2 lines there. And we do have 3 reactants that are all in the same state. So they're just going to be separated with commas instead of a line. Now, if one of those reactants was a solid or a liquid, for instance, then we would separate them using those lines. But here they're all in the same state, so we'll just keep them separated with commas. So we have permanganate, which is aqueous, manganese, which is aqueous, and hydrogen ions, which are also aqueous. So you'll notice here we included both reactants and products, but we did not include water because it's a pure liquid. So this is kind of similar to our gas or equilibrium expressions, but you'll notice we do include solids. So solids will be included here. All right, and then at the very end, we do have platinum as our electrode, so that will be included in our cell notation. But because it's in a different state from the reactants and products, we're going to separate it with a line. All right, so this might seem a little complex, but I promise this is easier than writing out both half reactions. So let's summarize what we learned about cell notation. So again, this is a shorthand representation of an electrochemical cell. And remember, oxidation will be on the left where the anode is, and then reduction will be on the right where the cathode is. And we separate those two different half reactions with 2 vertical lines. And then we saw that substances in different phases are separated by a single vertical line. So that represents the boundary between the phases. So as an example, we saw that solid iron was separated from aqueous iron 2 plus. So if you have a single line, that's a phase barrier. But we also saw that in some cases we might have multiple species that are in the same phase. So in that case, we'll just use a comma. All right. Now, another way to think of this is that the double line that we used is representative of the salt bridge, which connects the oxidation half-cell reaction to the reduction half-cell reaction. So typically, you can think of the cell notation as electrode for the oxidation state first, and then we put the electrolyte for the oxidation half reaction next. Then we use those two lines to separate oxidation from reduction. And then we write the electrolyte for the reduction half reaction. And then we put the electrode for the reduction half reaction. And we're separating the electrode from the electrolyte with a single line. All right. So actually, let's go back to this slide, and I'm going to use a different color, and we're going to write the cell notation for this electrochemical cell. So notation, I don't know what I was spelling. All right, so the oxidation reaction comes first, remember, and we want to list the electrode first. So let's put zinc solid, and then we're going to put a line, a vertical line, to separate it from the ion, zinc 2 plus, which is the aqueous component, so that's the electrolyte. And that's all there is for that side. So then we're going to put two vertical lines to separate oxidation from reduction. And then for the reduction, we're going to put the electrolyte first. So we want to put copper 2 plus first, and that's aqueous. And then we'll put another vertical line to separate that from the electrode, which is solid. So that's copper. Okay, so that's not too bad, right? Now some electrochemical cells are more complex than others. So we saw the permanganate example. That one was a little trickier. But I think we'll stop here today. Next time, we're going to discuss something called a standard reduction potential. And this is how we're actually going to calculate the standard electromotive force, or E cell, for an electrochemical cell. So I will see you in the next video.